Drift velocity. This diagram represents a wire with the positive ions and an electron here. You'll see there's a potential difference with this side being negatively charged relative to this side. So the electron might take a path something like this, with many collisions on its journey. In reality there'll be many electrons in the wire, all travelling to the right. And for simplicity we can ignore their collisions and assume that they travel something like this. To find the number passing, say, this point in a time t, we could mark the electrons at this point, allow them to travel for time t, and then mark this point. So this region contains the electrons that have passed this point in time t. Here we have the wire of length s. So the number of electrons passing this point in time t will be given by the density of electrons in this region, which we can call n, multiplied by the volume taken up by these conduction electrons, the volume of the wire in this region. The volume is given by the cross-sectional area A of the wire, multiplied by the distance travelled, s. But the distance travelled is given by Vt, where V is what we call the average drift velocity of the electrons. Each electron carries a charge E, and so the charge passing in time t will be given by the density of the electrons, multiplied by the cross-sectional area of the wire, multiplied by their average drift velocity, the time taken, and the charge carried by each electron. But the charge passing in time t is simply the rate of flow of charge, or the current, as delta Q over delta T. So this leads us to the equation I equals NAVE, where I is the current in amps, N is the number of charge carriers per cubic meter, A is the cross-sectional area of the conductor, V the mean drift velocity of the electrons, and E the charge on the electron, the magnitude of which is 1.6 times 10 to the minus 19 coulombs. Good conductors have a high density of conduction electrons. This means a large value of the number n. Insulators have very few or no conduction electrons. They have a low n. And semiconductors, such as silicon, will have an intermediate number of conduction electrons. Let's look at an example. A piece of copper wire of cross-sectional area 1 square millimeter carries a current of 2.5 amps. Calculate the mean drift velocity of the electrons. And we're told copper has an electron density of 8.47 times 10 to the 28 electrons per cubic meter. Okay, we start with the equation I equals NAVE. Then we rearrange for V as I over NAE. Then putting in the numbers, we have the current at 2.5 amps. The number of free electrons per cubic meter, 8.47 times 10 to the 28 per cubic meter. The area was 1 square millimeter. We need this in square meters, and it is 1 times 10 to the minus 6 square meters. And the magnitude of the charge on the electron, 1.6 times 10 to the minus 19 coulombs. This gives a drift velocity of 1.8 times 10 to the minus 4 meters per second. This is around 1/5 of a millimeter every second. This is actually their mean drift velocity. Between collisions, the electrons can be moving at speeds of around 10 to the 6 meters per second, but they actually travel along the wire at a very low velocity. Sometimes the more general form of the equation is used, where instead of using the charge on the electron E, the charge of the charge carriers Q is used. The equation then becomes I equals NAQV, where I is the current in amperes, N the charge density per cubic meter, A, the cross-sectional area, Q now the charge of the charge carriers, and V the drift velocity in meters per second. If the current was passing through copper sulfate solution, for instance, the charge carriers would be positive copper ions and sulfate ions. The copper ions would have lost 2 electrons and so have a charge of plus 2e, or plus 3.2 times 10 to the minus 19 coulombs, and the sulfate ions will have gained 2 electrons to have a charge of minus 2e, or minus 3.2 times 10 to the minus 19 coulombs.